All right, now simplifying radicals is an important key to a lot of the things we study in Chapter 8 on right triangles. So I'm going to give you a few examples of simplifying radicals into a simpler radical form. That doesn't mean a decimal, that just means a simpler form that still has a radical in it. Now our goal for simplifying radicals has to do with the square roots of perfect squares. Like the square root of 4 is 2, the square root of 9 is 3, the square root of 25 is 5, square root of 100 is 10. You get the idea. So when we have the square root of a perfect square, it gets pretty easy for us to simplify it. So we're looking for perfect squares as we are simplifying. So I will take 12 and make a factor tree with it. 12 is, let's see here, 3 times 4. And 4 is 2 times 2. Now, whichever factors you choose, you should still get 3, 2, and 2. So the square root of 12 is equal to the square root of 2 times 2 times 3. Now, since I have a pair here, the 2 and the 2, it gives me a perfect square. So I'm going to write this as 4 times 3. Now, if I have the square root of two things being multiplied, I can separate those into two separate square roots. Okay, and the square root of 4 I know to be 2, and the square root of 3 is still the square root of 3, and so this becomes, simplifies to be 2 square root of 3. Okay, now in practice, I don't usually go through all these steps because it takes too long. In practice, I do my factor tree, I find my pair. Now when I have a pair, that means I have a perfect square. And for that pair, I take one of those numbers and write them outside of my square root, and then whatever's left without a pair, without a perfect square, stays inside. So by 2, my pair of 2's, I have a 2 here, and the 3, I have a square root of 3. So we just jump from here to here. Let me give you an example of that. The square root of 90, now 90, I'll just pick 3 and 30. 30 is 3 and 10. 10 is 2 and 5. So I have a pair of 3 and 3. That means I have a perfect square. So I rewrite this as 3 from my pair of 3's, square root of what's left, 2 times 5. And 2 times 5 is 10, and so 3 root 10 is a simplified form of the square root of 90. Okay, so this, a little more complicated, 3 times 2 is 6, and the square root of 3 times the square root of 3 is the square root of 9. Okay, and the square root of 9 I know is 3, so 6 times 3 is equal to 18. Okay, now this next one's a little more complicated. 6 times root 2 is 6 root 2, and the square root of 2 times the square root of 2 is the square root of 4. Okay, I'll rewrite that down here. 6 root 2 over the square root of 4. Now, the square root of 4 is equal to 2. Oh, now 6 over 2 simplifies to be 3 over 1, and I got 3 root 2, which is a simpler form. 8.1 is about the Pythagorean Theorem. Okay, if a triangle is a right triangle, then the sum of the squares of the lengths of the legs is equal to the square of the length of the hypotenuse. Now, to me, that doesn't make as much sense as just thinking that if it's a right triangle, then a squared plus b squared equals c squared, where c is the hypotenuse. Okay, it only works for right triangles. Now, when a, b, and c are all whole numbers, we have what's called a Pythagorean triple. For example, 3, 4, and 5, 3 squared plus 4 squared equals 5 squared. They're all whole numbers. It's a Pythagorean triple. 5 squared plus 12 squared equals 13 squared. It's a Pythagorean triple. So when this happens, I'll refer to it as a Pythagorean triple. Okay, so the Pythagorean theorem is one of the most proved theorems, I think, in all of mathematics. There's hundreds of proofs that are slightly different, that show different reasons why a squared plus b squared equals c squared. Here's one example. Here's a triangle of the height is a, the length is b, and the hypotenuse is c. Now, if you look down here, this length down here is still c, and this length is c, and the shape of it is a square. So the length of this down here, well, sorry, the area of this is c squared. Okay, so these pieces together make up c squared. Keep that in mind. All right, now if I begin to move these lengths, the area is not going to change. So this big area is still equal to c squared. If I move this one as well, it's still equal to c squared. But an interesting thing happens. This length is a, and this length here is also a, and so the area of this square is a squared. And the length of this length is b, and this length up here is b, and so this square right here is b squared. So you can see that a squared plus b squared is equal to c squared. Here's an example. Find the length of the hypotenuse. I'll call the hypotenuse x, and since it's a right triangle, I know that a squared plus b squared is equal to c squared. Now c is always the hypotenuse. In this case, the hypotenuse is x, so c is x. A and b can be either 20 or 21, it doesn't matter. So 20 squared plus 21 squared is x squared. Now 21 is 400, sorry, 20 squared is 400. 21 squared is 441, which is equal to x squared. Okay, adding these together, 841 is equal to x squared. So let's see here, how do you undo a squared? You do a square root. So x is the square root of 841, which equals 29. Okay, it's a perfect whole number, and so 20, 21, and 29 are a Pythagorean triple. Okay, here's an example where we want to find one of the legs. Again, a squared plus b squared equals c squared works because it's a right triangle. Now, c is always the hypotenuse, so in this case, c is 20. Let's see here. I'll say x squared plus 8 squared is equal to 20 squared. X squared plus 6 squared is 64. 20 squared is 400. Now to solve for x squared, I'm going to subtract 64 from both sides of my equation. X squared is equal to 336. Okay, to simplify x squared, I get x is equal to the square root of 336. Now to simplify 336, I'll need to draw a factor tree. 336 is, let's see here, 3 times 112. 112 is 2 times 56. 56 is 7 times 8. 8 is 4 and 2, and 2 is 2 and 2. All right, so I have some pairs. I have this 2 and 2, and this 2 and 2. And so this simplifies to be 2 times 2, the square root of what's left, 3 times 7. And so I get 4 root 21. Okay, the converse of the Pythagorean theorem. Again, the Pythagorean theorem is if a squared plus b squared, the Pythagorean theorem is if it's a right triangle, then a squared plus b squared equals c squared. The converse, where you take those at if and the then and you switch them. So the converse is if a squared plus b squared equals c squared, then triangle ABC must be a right triangle. So, question, a triangle has side lengths 10, 24, and 26. Is the triangle a right triangle? Well, we can test to see if a squared plus b squared is equal to c squared. Now, of the three, the longest one's 26, so that must be c. So I'll say 10 squared plus 24 squared, and now I don't really know, so I don't want to put equals. I'm going to put equals with a question mark above it. Is equal to 26 squared. Okay, so 10 squared is 100. 24 squared, I don't know off the top of my head. 24 squared is 576, is equal to question mark 676. So 100 plus 676 is 676, and that's equal to 676. And so this must be a right triangle because it's equal. Okay, another example. A triangle has side lengths 6, 9, and 12. Is the triangle a right triangle? Again, I'll test a squared plus b squared to see if it's equal to c squared. Now, 12 is the longest, that must be c. 6 squared plus 9 squared is c. Is that equal to 12 squared? 6 squared is 36, 9 squared is 81, and 12 squared is 144. 36 plus 81 is 117, but that's not equal to 144. Okay, so this is not a right triangle. Now, one interesting idea we can think about is if it's not a right triangle, is it acute or is it obtuse? And the way I think about that is I think, is C too big or is it too small? In this case, it's too big. If it's too big, it is an obtuse triangle. Okay, so it's not a right triangle, it happens to be an obtuse triangle. Again, if C is too small or too short, then it will be an acute triangle. If C is too big or too long, it's an obtuse